All right, Honors Chem. Today we are going to learn a couple of new techniques, and it's going to be a lot of information. So hopefully you watched at least the first half of that video that I posted about weak acids and weak bases, and it talked a little bit about equilibrium. So the first thing that we really need to do is we're going to talk about equilibrium, and we're going to talk about constructing an equilibrium constant, and then we're going to get into the math of how we're going to do this. Okay, so we are also skipping around here. So we are at the bottom of page 215. It's a problem that we skipped earlier. This is example 4. It says, what is the hydrogen ion concentration and the hydroxide ion concentration of a solution of a weak base? We have ammonium hydroxide. If the original concentration, remember square brackets means concentration in moles per liter, molar. The original concentration of ammonium hydroxide is 0.65 molar. And then it has K sub B. What the heck is the K sub B? That is the equilibrium constant for this weak base. So let's talk about what we mean equilibrium first, and then we'll go into this equilibrium constant. So we're going to draw out the relationship between the ammonium hydroxide and then how it actually dissolves in water. So it's a weak base. So we will have ammonium hydroxide aqueous, and it will go to ammonium, the ion, and hydroxide, the ion. Now, because this is a weak base, we know it doesn't really dissociate all that well. So honestly, that forward reaction doesn't happen that much. In all reality, this backward reaction that I'm just putting a backward arrow on happens more. And that's why I made that backward arrow bigger. Remember, not all reactions go to completion. In fact, most reactions don't. Most reactions have an equilibrium where they are going back and forth. Now, when equilibrium is achieved, that means the rate of the forward reaction is equal to the rate of the backwards reaction or the reverse reaction. Now, the rates being equal mean that it is an equilibrium, but it doesn't mean that there are equal concentrations of both reactants and products. In this case, we know that because this equilibrium constant is less than 1, that the reactants are actually favored. We will actually have more reactants in this solution than we have products. And let me show you why. When we create an equilibrium constant like this, and this is a weak base constant, but in reality, it is an equilibrium constant. We always put, so when we say an equilibrium constant, we always put the concentration of the products. And remember, these are molar concentrations, moles per liter, over the concentration of the reactants. Now they have to be in concentrations, moles per liter. So we're all going moles per liter here. So the only thing that we can really put in equilibrium constants are things that are aqueous or gas. If they're solid, we can't get a concentration. If it's pure liquid, also, we cannot get a concentration. So the only things that we put in equilibrium constants or dissociation constants are those that are aqueous or either gas. Now, all of these, if you notice, are aqueous. So if we do the equilibrium constant, and I'm going to just say Kb because it is a base equilibrium, our products are the ammonium ion concentration and the hydroxide ion concentration. And our reactant is our ammonium hydroxide concentration, also aqueous. Now, you don't have to put the state in the brackets because it really is a mathematical concentration. Okay, so I'm going to just erase this a little bit because I need to have this go over on the side a little bit more. Now that we know how to write equilibrium constant, I'm going to show you a technique that we use to solve these kind of equations. Now, this technique is called a lot of chemists will call this an ice table. A lot of chemists will also call this a rice table. And you'll see why in just a minute. Now, we're going to make this grid here. And the very first thing we need to do before we even make the grid is we need to put the reaction on top. So I'm going to rewrite the reaction so that we can make a grid underneath it. And I'm going to move me up here so that I have some space to write. So we're going to rewrite this reaction. We have our ammonium hydroxide going back and forth, and mostly forth, right? No, mostly back, with ammonium and the hydroxide ion, okay? So there's our first level of our ice or our rice table. There's our reaction. So that's why some people call them rice tables. Our reaction, R. Our next line, we're going to make lines in between each of the products and each of the reactants, is I. And I stands, so R is for our reaction. I is for our initial concentration. Now remember, all these concentrations have to be molar, so they have to be moles per liter, okay? So our initial concentration, when we first put that ammonium hydroxide in there, is 0.65, okay? Now, when we first put that ammonium hydroxide in there, we have no ammonium and no hydroxide. We're going to start out with just ammonium hydroxide, okay? Then the next line is change. So C is our change in the concentration, okay? So if I start out with just ammonium hydroxide, that reaction, once it gets to equilibrium, has to produce some ammonium, and it has to produce some hydroxide ion. Would you say so? So we are at least going to produce some of this and some of this. So that means that for every ammonium hydroxide that is taken apart, right, I'm going to lose some ammonium hydroxides to make some ammonium ions and some hydroxide ions. So every one of those ammonium hydroxides that are taken apart, I'm making one ammonium ion and I'm making one hydroxide ion. So the ratio is when I lose an ammonium hydroxide, I make one ammonium ion and one hydroxide ion. So the stoichiometric ratios are really important. So you have to pay attention to those when you're assigning your X values, okay? And then the last line is E. This is my end concentration or my equilibrium concentration, okay? So my equilibrium concentration is really the sum of the I, my initial line, and the change line. So my equilibrium concentration is the sum of the I and the C line. I'm just summing it up. Okay, so I would have 0.65 minus X here. 0 plus X is just going to be X, and 0 plus X is still going to be X. Okay, so I'm going to put these equilibrium values that I just created, this, this, and this, and I'm going to put it into my equilibrium expression that I just did. Okay, so let's do the math here. So if I put it into my equilibrium expression, My products are on top. So for ammonium, I have X. And for hydroxide, I also have X. So what is X times X? It is X squared, is it not? Okay, so there's my products and my reactants. I'm going to have 0.65 minus X. And I'm going to set that all equal to my Kb. And my Kb is 1.8 times 10 to the negative 5. Okay? And from here on out, it really is just an algebra problem. And you're going, oh my gosh, if I have to take 1.8 times 10 to the negative 5 multiplied by the quantity 0.65 minus x and then equal to x squared, I'm going to have to use the quadratic equation. And yes, but no. The thing is, if I have an equilibrium constant, which I have here, that is less than 10 to the negative 3, it means that my negative x here on my 0.65 minus x is so small that it really isn't going to matter. So that 0.65 minus x, I can basically ignore that minus x. So as soon as my computer figures out what it's thinking about, this x right here is so small that I can ignore. I can just ignore it. So I'm going to ignore it. So I'm going to be nice to you guys, and I'm going to give you things like this where the equilibrium constant is so small that you can ignore the x. And I'm also going to give you perfect squares so you don't have to use the quadratic equation. Now, in AP chemistry and so on, your teachers will not be so nice. You will be using the quadratic equation. So it might behoove you, if you have a programmable calculator, to get the quadratic program put in your calculator. I know I have it in here. It makes it a lot easier. Okay, so here we go. Let's do the algebra. So I'm going to multiply both sides by 0.65. So if I multiply 1.8 times 10 to the negative 5 by 0.65, I get 1.17. 1.17 times 10 to the negative 5 is equal to x squared. And now all I have to do is take the square root of that. So I'm going to take the square root of that. So let's take the square root. So if I do that, x is equal to 3.4. Let's see, I've got how many digits? I've really got 2 digits. So 3.4 times 10 to the negative 3. That is my x. Now, I am not quite done. The question asked me what was the hydroxide concentration. So I do have that because that is x. So 3.4 times 10 to the negative 3, that is definitely my hydroxide ion concentration. Okay, so I do have that. I also want to know what my hydrogen ion concentration is. So, how do I do that? Isn't Kw equal to hydroxide times hydrogen ion? So if I have the hydroxide, couldn't I just divide this by my hydroxide to get my hydrogen? Remember, Kw is 10 to the negative 14. So here I go. I am going to divide 1 times 10 to the negative 14 to get my hydrogen ion concentration. So when I do that, my hydrogen ion concentration to, let's see, that's a horrible bracket. My hydrogen ion concentration to 2 significant figures, because that's really all I have, is 2.9 times 10 to the negative 12. Okay. Now I could follow up and be like, okay, was this an acidic or a basic solution? It's definitely basic because the hydrogen ion concentration is greater, or it's less than 10 to the negative 7. So it's definitely a basic solution. All right, so there's our first example. We're going to skip around a little bit to find our next example really quick. So, and I'm sorry that these aren't put together in your books. So come along with me. Okay, so here we go. So we are now on the bottom of page 218. So you're going to have to skip a couple of pages. So 218 at the bottom. These are going to be very much the same. Okay, so calculate the pH, the pOH, the hydrogen ion concentration, the hydroxide ion concentration in a 0.5 molar solution of acetic acid. The acid dissociation or equilibrium constant is 1.8 times 10 to the negative 5. Okay, so here we go. Same type of thing. First thing we've got to do is write our, what did you think? Our equation. So we're going to start with our acetic acid. Okay, so here is our R. Okay, so we have our acetic acid, HC2H3O2, and it's going to go back and forth and mostly back to hydrogen and the acetate ion. Okay, so there's our R line of our rice chart, our reaction. Okay, now let's create the rest of our chart here. Okay, we need our initial concentrations. We need our I. Okay, remember we're going for reaction, initial, and then our next line is going to be change. And then our last line is going to be our equilibrium or our end concentration. Okay? So our initial concentration, we're going to pretend that we just have acetic acid, straight acetic acid. And our concentration here is 0.5 molar. We're going to have 0 hydrogen and 0 acetate ion. Okay? So if we actually are going to achieve equilibrium, we've got to actually create some hydrogen and we've got to create some acetate ion. So for every acetic acid that gets ionized, right, this is going to go down. For every one of the acetic acids that gets ionized, I make 1 hydrogen and I make 1 acetate. Do you guys agree? We have a 1-to-1-to-1 ratio here in this reaction. Okay, so our equilibrium is going to be the sum of our initial and our change line. So 0.5 minus x, right? So I'm going to have 0.500 minus x, and 0 plus x is x, and 0 plus x is x. Okay, now just a little bit of, whoa, that's not what I wanted to do. I still want that line. Okay, our equilibrium constant here. Remember, when we do our equilibrium constants or our dissociation constants, it's our products on the top and our reactants on the bottom. So our products are hydrogen and the acetate ion, C2H3O2 negative, all divided by our reactants, which is our concentration of acetic acid. Okay? So now we can start plugging things in. So I'm going to plug this into here. Okay? And I'm going to plug these in here. And I'm going to plug this right here. Okay? Does that make sense? Okay, so here we go. Let's start plugging. So our equilibrium constant, we have 1.8 times 10 to the negative 5th. Okay, our hydrogen ion concentration is X. Our acetate ion concentration is also X, so X times X is X squared. And our equilibrium concentration of acetic acid is 0.500 minus X. Now notice that our equilibrium constant is less than 10 to the negative 3. So that means, once again, that I can ignore this X. Remember, the cutoff is 10 to the negative 3. So if our equilibrium constant Kb or Ka is less than 10 to the negative 3, we can ignore that X. So we're going to ignore it because that means we don't have to use the quadratic formula. And I like things being easy. Okay, so that means then we're going to take 0.5 and we're going to multiply it by 1.8 times 10 to the negative 5. I can get my calculator here. So that means we have 9.0 times 10 to the negative 6 is equal to X squared. Do you agree with that? Okay, so now we're going to take the square root of that. And that gives us 3 to the negative 3.0 to the negative 3 is our X. So we can plug this in. So we have 3.0 times 10 to the negative 3 here, and 3.0 times 10 to the negative 3. And let's see, 0.5 minus 3 times, so this would be 0.5 minus 0.003. Do you guys agree with that? Yeah? So this would give us a new concentration of 0.497 molar. Okay? So let's use these numbers to calculate our H, which we've already done. So here's our H concentration right there, right? We can use that to calculate our pH, right? So let's take our negative log of that, negative log of this to get our pH. So if I do negative log of that, 0.003, that gives me a pH. And I always like to go to the hundredths. So this would give me 2.52. Okay? Now I can get the pOH really quickly by just taking 14 minus that pH. So I'm going to do that. And I'm going to just use the whole kit and caboodle that I calculated here. I'm not even. So to the hundredths, and that's what I usually like to do, to the hundredths, that will give me 11.48. Okay, so I've now got the pH, I've got the pOH. So I've got the pH, I've got the pOH, and I've got the hydrogen. Now the last thing I've got to do is just get the hydroxide. And to do the hydroxide, I'm just going to do 10 to the negative pOH. Okay, and I'm going to use the whole thing that my calculator gave me. Okay, I'm not going to round it. So if I do 10 caret key, that gives me a pOH of 3 to the negative, let's see, is that really what I want? That gives me 3.00. Let's see, this is giving me 3 times 10 to the negative 12. But if I do the dissociation constant of water, gives me 3.33 times 10 to the negative 12. Okay, so let's see. I have two sig figs, so 3.3 times 10 to the negative 12. And my computer is thinking once again, so I can't write. So 3.3 times 10 to the negative 12. Okay, please. Okay, so this is how we use rice charts to get our calculations. Okay, and I have one more example once the computer will let me write. I have one more example of how to construct a rice chart and do our calculations. Okay, maybe give it another few seconds, and if it doesn't, I'm gonna